Previously, in our discussion of polynomial interpolation, we had made the observation that if I give you any collection of distinct x numbers, x0 through xn, and a polynomial of degree less than or equal to n, regardless of where these points came from or where the polynomial came from, you can write p of x as a constant plus a constant times x minus x0 plus a constant times x minus x0, x minus x1, all the way out to an times the product of n factors, 1 through n minus 1, together with that one. And this format is going to be exceedingly useful to us. In particular, if my x0 through xn numbers are actually the x coordinates out of a data set of an interpolating polynomial, our interpolating polynomial can be written in this form as well. As an example of this, think of having a data set with 3 points in it. The x coordinates are x0, x1, and x2, and we'll have corresponding function values. The first data point is x0 equals 1, f of x0, 2. The second data point is x1 equals 2, f of x1 equals 7. And lastly, x2 will be 6, while f of x2 will be 87. I claim that I can write the interpolating polynomial in this format. To know the interpolating polynomial, then, I just need to know the constants a0, a1, and a2. One of my data points has x coordinate equal to 1 and function value 2. That is to say, when I put x equal to 1 into my polynomial, I want to get 2 for an answer. 2 needs to be a0 plus a1 times 1 minus 1 plus a2 times 1 minus 1 times 1 minus 2. This factor is 0. This factor is 0. So this equation just says that 2 is equal to a0. We now know the a0. We may as well write it down. We'll write all the constants down as we go along. On the other hand, when x is equal to 2, the function value is supposed to be 7. So we want 7 to be the answer when we put x equal 2 into our polynomial. So 7 needs to equal a0, which we've previously figured out, plus a1 times x is now 2, 2 minus 1, plus a2 times x minus 1, x minus 2. The last term is 0 because of the factor 2 minus 2. 2 minus 1 is 1. 1 times a1 is a1. So this tells me that 7 and 2 plus a1 are the same number. Obviously, that means that a1 is 5. We now know not only the constant coefficient, but we know the coefficient of the x minus 1 factor. Notice I didn't say the linear factor because there's going to be a linear contribution from this term. Lastly, when x is equal to 6, the function value is supposed to be 87. Inserting that fact into the polynomial, I found out that this must be true. Now, none of these factors that we had literally had x minus x2 in them. This leads some people to believe that the last data point doesn't have any influence. But that's not right. Its influence is felt through this equation. Anyway, after you do all the arithmetic, it turns out that 60 and 20 times A2 are the same thing, meaning, of course, that A2 has to equal 3. Therefore, this is a polynomial of degree no more than 2 that interpolates a data set that has 3 data points in it. This is the interpolating polynomial. You'll notice that it isn't written in Lagrange form, but it is the same polynomial as if you had done a Lagrange form. This immediately suggests an algorithm. I'm going to think of my p of x as being the usual form, but let's be very explicit here. I'm going to be looking for this ai. Obviously, if you put x equals x0 into this, all of these factors are 0, except you'll have a 0 at the beginning. So to get started, to make your algorithm begin, you'll notice that a number 0 is nothing but the function value at x. Us that a0 is f of x0. We get a0 at no cost. So suppose we know some of the a numbers, possibly just one, a0, or maybe we know a lot of them, a0, a1, a2, up to a number I minus 1. And we're looking to get a number I next. So let's write out our polynomial in a form that's more conducive to this scenario. I'll write out the usual terms. There's going to be the term that has a number I minus 1 in it. That's the last term whose coefficient I actually know in this scenario. The next one will be ai times the product of x minus data x values with indexes that go from 0 to I minus 1. All terms after this are going to consist of a constant times a product of many factors, each one of which is going to have x minus xi in it. In that last formula, set x equal to xi. The p-value, if this truly is the interpolating polynomial, must be f evaluated at xi. So write that out. All of those terms that were beyond the term which contained ai will have a factor of x minus xi with x equaling xi. All of those later terms are going to have a factor of 0, so I can stop writing them down. They're not important to me. Also, the term that's going to tell me what the ai is ai times xi minus x0 times xi minus x1 out to xi minus xi minus 1. Because all of these x numbers are distinct, none of these factors are 0. That means I'll always be able to divide through by this quantity, so I'll be able to determine a number I. If I rearrange the terms slightly, f at x number I minus the terms that were at the beginning of the right-hand side previously must be equal to ai times this product, which I know to be a product of non-zero numbers. So this lets me divide through by that quantity without any worries. And if I know A0, A1, A2, up to AI minus 1, this formula is going to let me figure out what a number I is. So this obviously suggests an algorithm. Set a0 equal to f at x0, and for each value of I going from 1, 2 up to n, determine a number I by using this formula. At the end of this loop, you'll know all of the coefficients of the interpolating polynomial. We're going to adopt a new notation, though. I'm going to write f bracket x2, x4, x7 to be the coefficient of the quadratic term in the polynomial of degree no more than 2 that interpolates at the stated x values at x2, x4, and x7. Likewise, f bracket x6 comma x21 is the coefficient of the linear term that comes from the polynomial of degree no more than 1 that interpolates f at the 2 points x6 and x21. And in general, if I write f bracket xi plus 1 consecutive indexes to xk, this would be the coefficient of the k minus I pair in the polynomial that interpolates f at the stated x values. So far, we haven't actually done anything. This is just terminology. Or even in the simplest case, if I think about the polynomial of degree no more than 0 that interpolates at one data point, for example, the constant polynomial that interpolates f at x0, that would be the constant polynomial f of x0. When we write f bracket of x0, we're just speaking at a function value. More generally, f bracket xk is function value number k from the data set. So we already know some of these bracket quantities. We know the ones that are based on a single x value. If you think of this polynomial, if I cover this part up, this is the polynomial of degree 0 that interpolates f at x0. If I add on this piece, two things happen. Number one, when x is x0, this whole term is 0, and I still get the correct function value for f at x0. Because of the way we defined this, though, f bracket x0, x1 is the lead coefficient of the linear polynomial that interpolates f at both x0 and at x1. So if I stuck x1 into this polynomial, I would get f at x1 back again. In a similar way, we will tack on additional terms so as to get the interpolating polynomial that we're after. Once again, nothing much has been done yet. This is just terminology at the moment. We had started off speaking of these coefficients of these various products of linear factors as being a0, a1 out to an. In our new language, a0 is just f bracket x0. a1 is f bracket x0, x1, and so on and so forth. The last one will be f bracket x0, x1 out to xn, which is multiplied by the nth degree polynomial x minus x0 out to x minus x n minus 1. Many times people get confused about this indexing, though. If you started counting at x minus x1 and went up to the last term, That would be n-1 factors, that is. And then including that one, that would be n factors altogether. This polynomial, if you multiplied it out, which we're not going to, would start off with 1 times x to the n power. So this really is the nth degree part with associated lower order contributions. So f bracket x0 through xk is the ak from the original description. We want to have a way of computing these things. If we could get our hands on f bracket x0, which we can, and f bracket x0, x1, and f bracket x0, x1, x2, until we run out of x numbers, these numbers are a0, a1, a2, down to an. These are the coefficients of these various terms that we're going to add together. What follows is high trickery. Whoever thought of this the first time was an extremely clever person. We're going to say that we have a polynomial p that interpolates at xi plus 1 through xk. We're also going to have a polynomial q that interpolates at xi plus 1 through xk plus 1. These indexes, I plus 1 through k plus 1, are in a one-to-one correspondence with these indexes. If you add 1 to I, you get I plus 1. If you add 1 to k, you get k plus 1. The number of x values that I'm looking at here and the number of x values that I'm looking at here are the same. P and Q interpolate f at different places, but they're based on the same number of x data values. That could very well come across as gibberish. So, for example, P might interpolate the function at x3, x4, and x5. If so, Q would interpolate the function at x4, x5, and x6. Both P and Q interpolate at exactly 3 points, but they're not the same 3 points, although there is some overlap. We're going to make a new polynomial. We're going to call this r of x. R of x is going to be a fraction. The bottom of the fraction, though, is just a constant. It's xk plus 1 minus xi, which is not 0 because our data points are distinct in the x values. Upstairs, I'm going to take the polynomial that goes with the bigger indexed x values, and I'm going to multiply it by x minus the smallest indexed x value out of the entire collection. I'm going to subtract away the polynomial p of x, which interpolates my original data at the smaller indexes. This would be I through k rather than I plus 1 through k plus 1. I'll take that polynomial, multiply it by x minus x number k plus 1, and subtract. This is going to be a polynomial of degree that's at most 1 more than what the degree of p and q could be. This is seemingly a completely random thing to cook up, but let's do a little bit of investigating. R of x is this polynomial. So if I wanted to evaluate this polynomial r at x equals xi, I would replace this with xi, that with xi, that with xi, and that as well. If you do that, you can write down the result, and you immediately notice one thing. Upstairs in the first term, you have a factor of xi minus xi, so this first term is 0, and I don't care what q at xi is. Deleting the term that turned out to be 0, you'll notice that upstairs I have the negative of xi minus xk plus 1. That would be x number k plus 1 minus xi. So the numerator of this fraction is the same as the denominator. That's 1. So r at x number I is 1 multiplied by p evaluated at x number I. But remember, p interpolates f at xi through xk. So p of xi is f of xi. This R polynomial that we've cooked up interpolates the original data at x equal I, the smallest index of all these x's. What about the biggest index? What is R evaluated at x equals x number k plus 1? Again, I'm going to take my R polynomial formula and just replace the letter x with x number k plus 1. In this case, the second term has a factor that's 0. So this piece is 0. Xk plus 1 minus xi shows up as a factor upstairs and is also a factor downstairs. The xk plus 1 minus xi is going to cancel out. Having done so, we find out that r at x number k plus 1 is q at number k plus 1. Q interpolates function f at indexes I plus 1 through and including k plus 1. Q at x number k plus 1 is the function value that goes with x number k plus 1. This R polynomial interpolates the function f certainly at xi and also certainly at x number k plus 1. What about all the other indexes? P interpolates the function at xi plus 1 out to xk. Q interpolates the function at xi plus 1 out to xk, so including the xk here, xk plus 1, that is. Let j be one of these indexes in common that we haven't looked at yet. Let j be an index that's at least bigger than I, but has to be smaller than k plus 1. That index j is going to be an index for which p correctly interpolates the function, and q does as well. So I'm going to evaluate r at x number j this time. As before, any place you see an unindexed x in the r formula, just replace it with x number j. We just mentioned that at the kind of index we're looking at here, both p and q produce f at x number j when supplied with x number j as the input. So q at xj is f of xj. P of xj is also f of xj. Upstairs, both terms have a factor of f of xj, so I can factor that out front so that it doesn't distract me. Now, upstairs, I have xj minus xj. The xj cancels out. I have the negative of xi minus the negative of x number k plus 1, I have minus xi plus x number k plus 1, which is the same thing as x number k plus 1 minus xi. So for the indicated range of indexes, R evaluated at x number j is f evaluated at x number j times something divided by itself, which is 1. I know that the denominator isn't 0 because the x are distinct. So not only does this R function produce the correct function value at xi and at x number k plus 1 at any index between those two indexes, f, excuse me, the function value is going to be correctly reproduced by the R function. In this table that I'm going to draw, I'm drawing in the indexes at which the current polynomials that I have interpolate various x values. For instance, when I write 0, 1, 2, and 3, I'm thinking of the polynomials of degree 0 that interpolate the function at x0, x1, x2, and x3. We actually already know those polynomials of degree 0. They're just f at x0, f at x1, f at x2, and f of x3. What we have is a way of combining polynomials based on certain numbers of points to get polynomials of more points. I know how to take the polynomial that interpolates at x0 and at x1. I could put this into my R formula and get the polynomial that interpolates at x0 and at x1. I could take the information for polynomials that interpolate only at x1 and x2, use my R function, and find a polynomial that interpolates at x1 and x2, combining the information for x2 and x3, I could find a linear polynomial that interpolates at both x2 and x3. If you observe these two indexes, 0 and 1, if you increase both of them by 1, you get 1 and 2. If you take the 1 and the 2 and increase both of those by 1, you get 2 and 3. This is the kind of setup we need to have in order to take advantage of that R formula. If you take the polynomial that interpolates at x0 and x1 and the polynomial that interpolates at x1 and x2 and do the R procedure to them, you'll find a polynomial that interpolates at 0, 1, and 2. Take the polynomial that works at x1 and x2, the one that works at x2 and x3, combine using the R formula, and you'll get a polynomial that interpolates at x number 1, x number 2, and x number 3. But there you are again in that same circumstance. 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3. I can combine these two pieces of information using my R polynomial and get a polynomial that interpolates at I, 0, 1, 2, 2, 3. I'll have a polynomial that interpolates at x0, x1, x2, and x3, and that's going to be my interpolating polynomial. Called Neville's method. And Neville's method will be the thing that we easily modify to get the Newton divided difference method. So we're working with slightly more sophisticated ideas now than we have been in the past, but I hope this explanation is clear enough so that everyone can easily understand it. Next time, we will look at some detailed work with Neville. We will derive the Newton divided difference form, and depending on how the time goes, we may actually start looking at how one would program such a thing. Until then, I hope everyone has a good day. I'll talk to you again soon.